Let's take a look at an effect of the TD we are going to do today. Let's take a look. The effect is pretty obvious right away, right? What we are going to use here is a touch sensor to make a model switch and effect change. If I touch here, it will do an explosive effect of this model. And there will be a visual neon light effect, and then when it shrinks back, it will switch to another model. Explode again. This is the first one that we're going to do in this class. Second, besides just clicking the touch to trigger the effect change, what else can we do? We can also use another common interaction on our phones, which is the long press, right? We can also do long press. Okay, I'm going to press it now. It will switch the entire effect to a more cyberpunk-style wireframe effect. If I long press again, it will shrink back and return to this more realistic lighting effect. Hello everyone, welcome back to our GemSeed class. In the previous lesson, we talked about how to integrate our touch sensor into our TD. In this lesson, we will mainly focus on implementing a single trigger in TD and switching between models. There will also be a glare effect, a cyberpunk-style RGB delay effect, and a second type of trigger. This is the long press trigger, which can change the style of the entire scene, switching it to a wireframe format. Okay, let's open a brand new TD file and try this effect. Alright, now we've opened a new TD file and we're going to delete all the initial components. Now let's start by creating a few models that we'll be switching between. First, let's create a box. The default subdivision for our box is 24 points. We can open the small arrow on the right, then press the key W on the keyboard, and we can see the form of a wireframe with 24 points on it. If we want it to have more points, we can enable Use Division. Once we turn it on, we can add more points here. Let S add up to 13 points. In that case, we will open the instance for it shortly. When we instantiate it, each small block will correspond to each endpoint on the model. Then we'll deactivate its activation. Then, the very commonly used plugin here is the 3D to Point Cloud plugin. This is a plugin I created earlier. It's very useful. Here, we can connect our model's SOP component to it. Then, on the right side, we'll connect a null here. This will give us a point cloud that we can use. Then we can also customize the number of points in the 2.0 version of the plugin. But here we don't need to adjust the number of points. We can just proceed with the operations from there. You can also change its location here. We can see by going to the right to the top view and then clicking on Viewer Active on the right. Then, by pressing the V key on the keyboard, we can actually see each endpoint. Each endpoint corresponds to some point clouds in the three-dimensional space coordinates. We can use this plugin to control the point cloud's position, such as moving it up and down along the y-axis. It can be moved along the x-axis and z-axis. Both rotation and size can be adjusted directly in the plugin. This is our first model. Now, let's move on to the second one. Next model, we'll use a sphere. We create a sphere which is essentially a ball. Alright, let's connect the sphere. Delete the box. Alright, similarly, the sphere has also been converted into a point cloud form. Next, let's move on to the donut. We search for it, and it seems to be called a torus. Let's hook it up. Alright, now this has also been converted into a point cloud. Next, let's add something called a tube. Let's connect the tube as well. Okay, the entire effect is achieved by switching between point clouds. In other words, we use the switch node to toggle between these components. We right-click on them, select all three, and then drag them directly into the switch. All three of them are connected here. Then we can add a null after the switch. This is an empty node. After adding a null behind it, we can then use the null. It's best to develop this as a good habit. With this setup, we can add many more components in between the null. Usually we will add a null at the end of each operation. Alright, let's display this null. Alright, the principle we just mentioned is actually achieved by using the switch to toggle between these 4-point clouds. In the switch, if we adjust the index, we can see that the 4 of them are switched between. To make the transition smoother, we need to enable the blend option in the switch, which is blend between inputs. Once it's enabled, you'll notice a smooth change between the point clouds, with a fade-in and fade-out effect between each transition. But when we switch, notice how the transition happens. It's actually not as smooth as we expected, right? Why? If we take a look, it was actually mentioned in the previous tutorial. You can see if we click the middle mouse button on null 1, this represents the point cloud of the box model, and it has a total of 2,756 points here in the pixels section. The model has a total of 2,756 points, while the sphere model has just over 700 points. The donut has just over 800 points, and the tube has around 400 points. So, these 4 models have completely different sizes. Different sizes cause a problem. This causes an issue where extra or missing points occur during each transition. So, where do these points go? The computer doesn't know either, right? So it will have the kind of non-silky situation that we just saw. In this case, it's actually easy to solve. We can simply delete these nulls first. We'll ensure all point clouds have the same size and uniform pixel values. We'll standardize them to the same pixel value, ensuring consistency when switching between them. We'll use this fit node to standardize. As the name suggests, the fit node adjusts the pixel size of the top component. It had over 700 pixels. After applying the fit node, it's been adjusted. It has been scaled to a 1000 by 1000 resolution, resulting in a much larger pixel value. By default, it's set to 1000 by 1000, but we need to write an expression to change it. We'll write an expression here to fetch the pixel value of null 1. Op. Then add 2 parentheses. Note that the parentheses must be in English input mode. Then, between the 2 single quotes, we input the name of the component whose value we want to fetch, which is null 1. Finally, add a dot, and then we need to specify which value we want to fetch from it. It's called width, which refers to its width. Alright, then copy this and go to the height section. Change width to height, which refers to its height. With this, we've successfully fetched the pixel values of null 1. Next, go to the fit node and change fit best to native pixel. This way, the central part will still maintain its original pixel size, which is just over 700. As for the extra surrounding areas, to fully utilize the extra space and increase the number of points, which will result in a better visual effect, right? Then we can enter the sphere, and we also need to subdivide it a bit more to increase its complexity. Then, in the detail, we need to adjust its rows and columns. We adjust its width, the horizontal edge, and the vertical edge. Let's take a look. To help everyone understand better, let's change the rows to 52. Then, let's change the height to 52 as well. Now, we can see that it is almost completely filled. If we click on the sphere with the middle mouse button, we can see that it has over 2,600 points, while the box has over 2,700 points. Now, this ball has more than 2,600 points, and it could have even more. Let's change it to a 53 and a 53 and try it. 2705 for the sphere, and 2744 for the box. Now, if we add more, the pixel value might exceed that of the box. Now, it should be in a state where both sides fit together perfectly. Okay, let's make 2 copies of this fit directly, and then connect these 2 components to it. Then, let's replace these 2, replacing the original ones as well. Okay, following the same logic, let's change the rows and columns of this donut to 53 by 53. It's too much. It's 2,800 now. Let's change it to 52 instead. Still a bit too many, just 52. 2704. Okay, for this one, we also need to increase the subdivision and change it to 52 by 52 to see how it works. 2704. Let's take another look if we go to switch it again at this time. Compared to before, it should be much smoother now because each point has its own destination. Okay, let's continue. Okay, let's render it now. Let's create another small box. Let's create the most basic model for our instance, then add a transform behind the box to scale it down a bit. We narrowed it down to a 0.01. Try it, and then we'll add a geo behind it. Add a geometry, then a camera, and finally light. And then render, we render it out. Finally, we add one more null. Then, let's add a black background using the RGB key to create a black background. Then, click on the blue dot on null 2, and it will render in our background. A little too small. Let's scale it up a bit. Try setting it to 0.04 or 0.05. Alright, let's try it first. Let's move these forward, as we'll need this space later. Then, let's name it null 5 and rename it to POS, which stands for position. It's our position information, right? Then, open the instance in the geo and drag POS into the translate. We need to map this position to the corresponding part of its location. The X corresponds to the red R in the pixel, Y corresponds to green G, and Z corresponds to blue B, right? You can go to my previous tutorial about this point cloud. The tutorial will explain in great detail why this is R, this is G, and this is B, including in the GemSeed class. I will also explain in very simple and easy to understand language how the effect is achieved here. Alright, the entire effect has now appeared. We have mapped the small cubes to each of the small points we just saw. Okay, at this time we come to the switch. If we switch the index, we can see that it will continue to change, right? Alright, let's make the lighting a bit more dynamic. Find the light, then click the plus sign in the bottom right corner. Then, let's rotate it to the side. Now our light will be a side light. Then we can enable the shadow. You can choose either hard or soft. The soft shadow will use slightly more of your computer's resources. You can use soft shadow and increase the shadow resolution. By increasing it, the quality of the projection pixels will improve. Next, let's create a material here, foam. This is the best component to use when working with lighting and shadow effects. Let's drag the foam material onto our geo. Okay, now I want to create another light specifically to illuminate the side of our model, that is, its darker areas. Let's make sure the dark areas aren't too pitch black. So, for this part, we'll turn off the shadow. Then, let's lower the light intensity a bit, set it to 0.3. That should be enough to ensure the dark areas aren't too pitch black. Next, let's create a ground for it here. Why? Because, as we can see, even though we've added lighting, but it doesn't have the shadow. Can't cast a shadow onto the ground. Let's create a grid here to serve as a flat surface for our ground. Then, let's change the orientation to a ZX direction. That way, it will be a flat surface, and then we can change its size to 100. Make it very large, and then let's create another geo. Then in this case, our ground is rendered. Why is this scene half black and half white? Because our plane is by default at the center. The top is above our plane, and the bottom is below our plane. Then the light is blocked below. So we need to adjust the grid down a bit. Let's move it down by -1. Moving it down by -1 essentially shifts it slightly from top to bottom. Now, our model should be fully visible. Okay, now let's add some subdivisions to our grid, because later we'll be creating a wireframe visual effect for it. Let's change the rows and columns to 100 by 100. Alright, now our model feels a bit too static. It's just staying there without any movement. We can select all 4 plugins here. Right-click to select all, then go to the point cloud position under rotation and scale. Here, in the model's rotation, we can write an expression called epstime.seconds, and then press enter so that it will give us a constantly changing value. But now it's a little slow. We multiply it by a 10 in the back, and it will get faster. I want it to rotate on all 3 axes, so we'll copy all of this here, and it can achieve this effect of rotation. And then we bring it up a little bit. Okay, go up a little more. Okay, this is probably in the center of our picture. You can make the dark part of it a little brighter. Just don't let it be too pitch black. Then, let's position it above our plane. You can adjust it yourself and tweak the lighting in the dark areas. Okay, and then we make the square a little bit bigger. Yes, and now we're going to do a little interaction, which is to switch our model. To implement this switch, let's create a keyboard in Chop, which will bring in the values from our mouse. Every time we press 1 on the keyboard, it will trigger the event. We add a count after it. Okay, add a count, and then in the count we change the limit to loop. That way, it's a default loop counter from 0 to 10. When it reaches 10, it will reset back to 0. Let's see how many we have here. 0, 1, 2, 3, so here the count should be set to 3. Remember, in computing, we start counting from 0, not 1. Alright, then let's continue by adding a null after the count. Alright, this null will be used to control our switch. Let's first open the plus sign in the bottom right corner to map this data. Then, drag the value to the index of the switch. Now, if we press the 1 key on the keyboard, it will continue to switch. But there is no transition between switching it now. Since our data doesn't have any transition and is just constantly changing in a repetitive way, let's add a filter in between. Let's switch again, great, right? It's great to go from 0 to 3, but what happens if you go from 3 back to 0? Many students have encountered such a situation. Some students often come to ask me how to solve this situation. We have no problem from 0 to 1, 2, and 3, but when we come back, he doesn't know our number. From 3 back to 0, it passes through 2 and 1, which is why we get the situation we saw earlier. At this time, I usually make a new switch. Here we first create a switch by right-clicking on the line. What is this used for? Exactly, it's used to smooth out the transition between the switches. After the switch, let's create a noise by pressing the middle mouse button. What does this do? This will allow us to switch to noise before each change, making it burst out first. Then we can skip the transition part in the middle. It will then transition into our final model. Next, let's adjust the noise data. Turn off the monochrome setting to give it color. Then, in the output, let's change the RGB to a noise. That way, it won't inherit the previous pixel values. Then, in the noise, set the offset to 0 and increase the amplitude a bit to see how it looks. Then we connect the noise to this position. Don't forget to enable the blend in the switch as well. Let's think about how to deal with this data. We need to control two switches. First, let's make the switch on the right, switch to, change to noise. And then in the process, the first switch needs to complete its switching, and then our switch switches back to the input of the original model. Here we use a trigger, and we add a null after keyboarding. This way, it will be easier to switch our input later using the keyboarding before it. After null 4, let's create a trigger by pressing the middle mouse button. Okay, let's go to trigger, let's adjust its data. First, for the attack, set the attack length to 0. This way, it won't have a data transition from 0 to 1. We will adjust the data change later. We change peak length here to a 2. And then change sustain here to all 0. In this case, it is a... Now, if I press 1 on the keyboard, it will trigger a data change that stays at 1 for 2 seconds before it stops. Right? The 2-second pause is enough for our filter to complete the transition. In fact, we don't need filter because we don't need any transition between them, right? Then we add a lag after it. Lag and filter have similar meanings. But the difference is that it allows you to customize the easing in and easing out of values. Let's set the increase to 1. And decrease by 2 seconds. That means it takes 1 second to reach the maximum during the increase, and when it returns from 1 to 0, it takes 2 seconds, making it slower. Let's try it out. This is for 1 second, and when it returns, it will be slower, taking 2 seconds. Then, let's add a null at the end to control the switch value. We'll throw it in and give it a try. Seems to mean that, doesn't it? When we change from 3 to 0 again this time, let's take a look. There won't be the effect just now. Okay, now let's continue fine-tuning the specific parameters of the noise during the switching process. First, let's increase the amplitude a bit. Then, let's make the explosion more scattered. We can go to the switch and set it to a value larger than 1. So we can see a state of this noise. We'll switch it back later. Next, go to the transform, add an animation, and for the y-axis, use abstime.seconds. Yes, it's the same code as before, but using the default settings will make it too fast. Let's slow it down a bit. Try dividing it by 10. It's still a bit too fast. Dividing by 50 seems to be just right. Let's go to the switch and change the index back to the expression form we had earlier. Click the small blue square. Then let's try to switch again at this time. Okay, that seems to be right? Now let's fine-tune the size of these three models. Now the ball is a little too big. The size of these four models is a little inconsistent. Let's go to the plugin and find the size of the model directly. Let's shrink it a little bit. Okay, and then continue. We switch to donuts. We can shrink the donut a little bit, and then shrink a little bit, and then the tube. Let's make it a little smaller. These four sizes should be about the same size. Let's go and add some more details to it. In fact, when we do all kinds of projects, we start with a simple content and a foundation. Then, little by little, we'll make our entire component and system more complex, making the visuals more intricate as well. Okay, we see what we can add to it. Now, let's go into the geo and check the instance. We've only mapped its position for the instance so far, meaning we can control its location. Such as rotate. Can we make it when it explodes? We can see that after each square explodes, one of their directions is still the same. It doesn't feel so cluttered. We want it to be a mess when it explodes, right? We can also add some of this messy feeling to it here in Rotate Right. We go to Switch here, and we press the middle mouse button to create a noise. This noise is used as a component of the rotation mapping of our entire rotate. Let's go to the noise and change the output to a simple noise. We don't inherit its original pixel. We only inherit its pixel size. And then we turn off the monochrome. In that case, it will be a colored noise. So the distribution of its RGB values will be more dispersed. Then in offset, we pull it to 0 and let it return to 0. Then let's add a null at the end and call it rot, which is short for rotate. Then, let's drag rot into the rotate OP and correspond it to the RGB values. We see that there is no change now. Since the amplitude here is only 0.5, each small cube will likely rotate randomly by just 0.5 degrees. We can't see any difference at all. Generally speaking, this model can rotate up to 360 degrees, right? Let's change it to 360. Is it going to be a mess? In fact, we can click the small plus sign on this value. And then we can right-click pixel values. We can see it in the lower left corner. These data correspond to 1. R is our corresponding x-axis. Its random is a negative 479 degrees. G is a negative 234 degrees. That includes the blue, which corresponds to the z-axis, and it also has a random value. It uses the random values from this to map to the position of each small cube or sphere, allowing them to move randomly like this. But what do we want? We want it to be a 0 when it doesn't switch. It doesn't want it to rotate. Only when it switches, we let it rotate to a random 360 degrees. What do? We still use trigger. The trigger we just used. Remember our trigger from earlier? When we trigger it during the explosion phase, to set to 1, and after it finishes, it resets back to 0. This is actually what we want. Only when it explodes will it change, and we will use trigger at this time. We press the middle mouse button directly behind the lag to create a math. For the range, 180 should be enough. We don't need to make it so exaggerated. 180 is enough. Then we add a null at the end. We map null 6 to noise 2, which controls the rotate. Let's go to the amplitude and try it out. Make it explode. Is it right? When it explodes, the direction of rotation of all the squares is changing randomly. What else can we do? Let's go to transform and write the expression of abstime.seconds. Make it more random. We can multiply it by another 10 to make it faster. Let's give it a try. It's too fast to multiply by 10. Do it again. Now I think the effect is good. Okay, what else do we have besides the rotation we just saw? What does scale mean? Size. All of our models have the same size of small squares. We want the small squares to become more random when it explodes. It is absolutely possible. We directly copy and paste the two components of the rot, and then change the rot to a scale. Then we throw scale on scale op, and then give it the corresponding RGB. But now what? It's all gone. Since we're still using the noise that controls rotation, let's change the offset to 1 here. So that all the sizes are 1 by default, right? What else is there? Then control amplitude. We don't want it to drop 360 all of a sudden. This model is too big. This model is too big if is up to 360. Let's save it first. Is too big. We go directly to the math that controls rotate just now. We copy and paste it out. And then math here we make it a little smaller, change it to a 2, and then it become a change from 0 to 2. Let's try to reassign the value of null 7 to the amplitude of noise 3. This effect is almost the same. But what we just saw is that some of them have become rectangular. Why? Because now we have a random change of the 3 axes of RGB. So if we want the proportion of the volume of all the models here to be correct, we will use all the value of R directly. We will use all the value of R directly. Let's zoom in. In this case, we can see that it is such a random change. It's right. Okay, let's go on. Let's do some visual optimization for it. Let's add a bloom to it. This is a new component that appeared in version 23, and bloom is very useful. It can see the effect that we add this glare to us. We can adjust it at the pre-black level. To control the size of this halo, we don't have to adjust the size of the halo anywhere else. We can actually control it by adjusting it here. So what else can we do here? We can also, for example, make our halo bigger the moment we explode. Let it have the feeling of flash exposure and then change back. Or we can directly use the thing we just did. Similarly, let's copy a math node and use it to control this. For example, if we want it to not be so bright under normal conditions, to make it less bright, let's set it to 0.7. We'll change the 0 position to 0.7. During the explosion, let's set the brightness to 0.65. Then drag this value to the bloom. Now I think the effect may be good. Try again. Okay, what else can we do? You can also use an official plugin called RGB Delay. It is in the image filter. Here we find a component called Delay, which is the official plugin for us. It allows us to see here that the R channel, the G channel, and the B channel, that means by causing a time offset between the red, green, and blue channels, we achieve the effect we see in the current image. Exactly, it gives off a glitchy kind of vibe. Let's drag it up and replace it. We can already see the effect now. Similarly, if we want an interactive change here, actually, we just need to control the delay duration, and that should be enough. control the delay duration directly. Okay, let's take a look at one of the principles of the ROB delay. If we adjust this value, we will understand. For example, let me now adjust the delay of the red delay. As you can see, it causes a smear in your red channel, right? So in fact, we create it here and we do it again. We'll just go ahead and copy this out to control our ROB delay. Here we are. If we zero out all the 3 channels of delay, there is actually no delay, right? In fact, there is no delay. So when we get here, first 0, we don't let it change, and then when we get to 1, we directly let it go to delay to 15 dot, which means that after we explode, it goes up to 15. Let's try it. Let's map it directly to our piece and then our B piece. And then we take the 1 in the middle and make it negative. So it's a -15, let's blow it up. We can see that it has such an effect after the explosion. We just saw that the G channel has no delay, so it has no effect. We will also copy a special G channel for us, that is, the green channel, to make an effect. Here we use a -7 to take an approximate middle value so that it can be interspersed between R and B. And we give it up. Let's try again. Now we see that it's a delay with 3 elements of red, green, and blue, right? So if we want it to have a little bit of delay at this stage, let it not be so monotonous. Don't be so white. What can we do? In front of this value, for example, we add a 3 in front of it. We let it have a little bit of delay, 3 to this number, and then, for example, we go to the B channel here. Let's try it again. Now we actually have a little bit of a delay effect, right? A little bit, and then we let him explode again. Good. Now this is how to achieve the effect of a delay. I also want to make its halo a little stronger. Let's try changing it to 0.6. I think it's not bad. Our grid forgot to give it a material. We give it a material. Then we can go to the Phong material and adjust the emit to tweak its overall brightness. Let's adjust it just a little. It seems that you don't need to adjust it, and it's fine like this. You try to explode again. So let's go on. We have now achieved the first interaction, which is to let it achieve such a switch, right? What is the second interaction? Let's recall that the second interaction is actually a detection of long press. Here we go directly to our data. How to do the long press detection. Let's think about a long press, meaning we need to check if our trigger is constantly in the 1 state, right? If it just presses like this, it's not called long press. At least it's called long press for 2 seconds. So it's very simple to teach you here. Actually, here, after the null, let's create a filter by pressing the middle mouse button. With the filter, it will transform a sudden change from 0 to 1 into a smooth transition from 0 to 1, right? We change the 1-second transition to a 2-second transition. Then we add a logic to the back. What is the function of logic? It means that it can trigger only when the input value reaches a certain standard. Let's go to convert input and change it to the third. Off when outside bounds is a component I often use. We change the bounds to 1, which means that it will trigger only when it detects that the input is the 1. Let's take a look. Now I can only trigger logic after pressing it for 2 seconds. In fact, we have already achieved a long press trigger, right? We're checking that if we press it once, it won't trigger, and pressing it again won't trigger either. It will only trigger if I hold it down for 2 seconds. In this way, a detection of a long press is realized. Okay. Okay, so we use this to implement our stylized switch. Okay, we're gonna switch styles. What do we do first? Let's make our second style first, right? Let's make the second style first, and we copy the geo, and our second one is oil. Let's render. In fact, this is a material switch. We used a line material. For the second geo, let's render the second material by assigning the line mat to it. Including the ground, we have to copy it out, and only line mat has to be copied up. Let's add a cross X to disable both geos for easier observation. First of all, let's adjust the material of line. Now line is a little too thick, right? Let's adjust it. Let's turn it up to 36 in the distance far. What does distance near and distance far mean? In fact, it is a standard used to judge the thickness of our lines. That is to say, when my line is at 2.9, it will be thick until it reaches 3.6. It may have been getting thinner all the time. Alright, let's make it a little thinner as a whole. Let's change the width near, which controls the line length for areas close to the camera, to 0.4. For the far part, make it thinner by setting it to 0.1. In this way, we can achieve the effect of a near thick and far thin, which is similar to a near big and far small. Okay, let's continue. Now go to the point section and add some small accent dots to it. And we open the drawer points, so it will create a lot of endpoints for us. For the endpoints, let's increase the size of the dots. Set it to 5. We can see that there are a lot of these little dots on it, right? Let's try to switch at this time. The effect is quite good. Okay, so let's continue. So how do we achieve a switch between these two styles? In this place, we use two renders. The two renders are essentially one for rendering the first material's geo, and the second for rendering the second material's geo. We can give the geo a name here. For example, the first geo has the Fong material. Add a space and P to differentiate it as the geo with the Fong material. The second one uses this line segment. That's line, and we put a space plus L. The first one is P, and he will help us change it to P1. And then the second one is L, and he will change it to L1. Okay, now let's take these two geo that we just turned off. Untie them. In the first render, we see the geometry here, and we just need it to render something. Right, we only need to render the first material, which is Fong. Actually, we can input the geo name and add a small underscore. And then we add a P. This means that all geos with the prefix geo underscore will be rendered here. Now, we can see that it has been rendered. Now, only the first Fong material remains. Similarly, for the second one, here we use geo underscore L, followed by an asterisk. This will render only the wireframe. So here we just need to switch between these two pictures, right? But we still remember what our previous picture was like. It was a circle. A state of continuous expansion from inside to outside. In fact, this is also very simple. We add a circle directly after the second render. Then, let's change the operation in the output to multiply. What does that mean? It is the function of a mask. Because our circle is a pure white circle. When it is multiplied by our picture, all the multiplication is 1. It appears in the 0 state when multiplied by the transparent base, making it invisible. This achieves the current effect similar to a mask. We can go to softness here, and we will soften its edges a little bit. Basically, we control the size of the circle Using the radius to achieve this effect, we can directly expand it to about 0.8 to achieve the desired result. Here we use these components we just used to realize it. Okay, here we see that we have just implemented a long press judgment here, right? Okay, let's add a count after logic. In the same way, we go to count and change it to loop, and then change it to a loop of 0 to 1. In this way, it can realize a switch of long press. Let's go down a little bit, and then we'll add a lag after it. This is used to smooth our data. Set it to 1 for faster increase, and 2 for slower shrink. Then add a null after it. There is a math. Don't forget, math is used to control the size of our data, allowing the circle to change from 0 to 0.8. Then we activate null 11 and map its data to radius. Let's check it here. Long press the keyboard and it will shrink. We press the keyboard for a long time. It has undergone such an expansive change. Okay, let's move them all back a little bit. Finally, we use an over. Take these two pictures and superimpose them together. But how about it? There is a problem, right? The background here is transparent, so when the two objects overlap, the one behind will still be visible through the transparent background. So we're going to move RIP key forward and move ROB key all the way forward. So we're going to create an ROB key between them. They all have a black background. The order of over is wrong. Let's change the order. Let's try it again now. We have achieved the effect we just mentioned, but there is still a little flaw. When we switch back to the Phong material, we can see many little shadows left behind. Why is this? This is because, even though the points are gone, their projection onto the light is still being rendered. How can we fix this? We go directly to line material. For the point size, when it's set to 0, meaning when it's using the Phong material, we can change it to 0. When it's active, we can set it to 5. This way, we can directly create a new math function to control this. When it's 0, it stays in the current state, which is 0. When it's 1, it will be set to 5. Then we can try mapping it and see how it works. Okay, it's gone now. Let's try to press it again for a long time. Okay, so good, we have actually achieved this effect now. The 4 models here are system models. If you have your own interesting models, you can use them too. If you want to make some switches here, there is no problem at all. This is the best thing about TD, that is, its expansibility is very strong, right? We can replace your self-designed model or what you want to express at will. For example, you can put a model of a tree here, or you can put a person's head portrait. Of course, we must pay attention to our points here. If this point is too big, your computer will be stuck, including here. If a small box is used, it has 24 points. Takes up resources. Generally, I will create a box by myself. This box is actually to create a default box on C4D, but there are only 8 points. In fact, if I replace it, it will save more computer resources. When you go to use some more complex models as the original of our mapping, if you have a basic model here, its points must be the smaller the better. Because the computation of the whole computer is actually 8 points multiplied by 2756 here. So many points have to be rendered here. If I use 24 here, then if 24 by 2756, this is a direct tripling, right? It's too big. Our last part is replacing the keyboard with the touch sensor. Replaces, we actually talked about it last time. How do we use serial to connect our touch sensor to it? Select the corresponding COM value, then keep only one line in the received data. Then we go through a select later. Then select that line by selecting the index. Of course, I don't have our sensor here. Then, at the end, we can use a DAT2 to convert it into our desired data format. By using a DAT2, we can convert it into the desired data format. Then, when it's triggered here, it will go through a transition from 0 to 1. Finally, by using a math operator, we can convert it to a transition from 1 to 0, reversing the effect. Our touch sensor is called channel pair by default. But all the names we use here are a K1, which is a K1 of our keyboard. So we must use another rename here to change its name, otherwise everything behind us will report an error. Okay, let's just replace it here. At this time, when I touch my sensor, the data will change directly. The whole sensing system is built in this way. Alright, that's the end of our class. If you have any questions about Touchdesigner, you can join my Discord to ask me questions and I will do my best to answer them all.